Yay, all right. Hey, thanks everybody for coming. This is super exciting to be here. It's been a few years since I've had a talk here at DEF CON, and it's great to be back. I'm Michael Ossmann of Great Scott Gadgets, and I make hardware for hackers. So, you know, I spend my time completely devoted to building open source hardware, primarily for the information security community and for other innovative people. So, this is the NSA Playset RF Retroreflectors. Hopefully some of you have noticed this isn't the only NSA Playset talk on the schedule. Some of my cohorts are in the front row here, and we have talks coming up soon. The concept of the NSA Playset is, now that the ANT catalog has leaked, and it leaked last winter, we in the open security community suddenly have a glimpse of what the NSA uses, at least in some cases, for their hardware and software as you know, attack tools and the implants. Hopefully some of you have seen. The concept of the NSA Playset is that now that we know those things, let's build them ourselves. Let's create similar capabilities using open source hardware and open source software, or off-the-shelf hardware, anything that's readily available, very accessible. Try to make this stuff easy to use and try to raise awareness about the security implications that of these technologies existing at all. I gave a talk with Dean Pierce, who's in the front row here, at Tour Camp. And the URL's up there. You might be able to read it. Color is a little off, but most of my slides are black and white anyway, so who cares? If you're interested in a little bit of a background in the NSA Playset and a broad overview of what's in the ANT catalog and how we think these things can be made in the open community, that's the best place to start. That's the introduction talk to the series. And this weekend here at DEF CON, a number of us are doing talks on on specific parts of the NSA Playset. Today I'm talking about RF retroreflectors. Oh, and last night, by the way, how many of you were at the EFF summit? The summit last night? Yeah? Really? That's it? At the summit, I know a lot of you were there, and a bunch of us from the NSA Playset cabal got together and donated a whole bunch of hardware. So we made this cool Playset bucket. It's got HackRFs in it, and it has IMEs, and it has PCI Express attack tools and Thunderbolt attack tools. It has a hard drive full of rainbow tables for GSM. I mean, just on and on and on. Huge kit, and it went for $2,250 in the auction last night. So thanks to everyone who contributed and who bid on it. Is the winner of the auction here? No? Oh, well, I'd like to shake your hand at some point. That was pretty amazing that we were able to pull together and do that. So my talk today is on the RF retroreflectors, similar to those that are in the ANT catalog. And an RF retroreflector is well, and I've never heard the term RF retroreflector really before the ANT catalog leaked, so I've kind of adopted it. But it's a little implant that modulates an incoming radio signal and reflects it back to the radar device that's illuminating it. So the attacker's on the left, and the attacker fires a radio wave at the target. The target has a little implant that reflects that radio wave back to the radar unit being used by the attacker. The process of irradiating a target is often called illumination. You can kind of think of it as shining a light on the target, except the light happens to be radio wavelengths instead of visible wavelengths. But otherwise, it's the same thing. You're shining a radar beam at a target, illuminating it, and seeing what gets reflected back. And then the implant is some very small device that is designed to modulate the reflection. And this can be done at extremely low power, which is one of the reasons that this approach is useful. It can be done with no battery, for example. It can be completely powered just by the radio wave itself. So it's a super simple kind of implant design that is very low power and uses a very small number of components. So it can be tiny and it can be without any local battery source. So that's the kind of thing I'm talking about today. And I kind of want to set the record straight a little bit. One of my earlier talks got some press, and people were writing that I was reverse engineering tools in the NSA ANT catalog, and I don't think that's actually correct. I don't have any devices from the NSA. I don't have any inside knowledge of devices used by the NSA. All I have is the information that's in the public leaked ANT catalog that anyone can find, leaked on the internet. So I don't really feel that I'm reverse engineering the NSA's tools. I'm forward engineering tools that have similar capabilities to those that the NSA uses. And hopefully this will help us in the open community create a set of tools that we can use to research this kind of capability and find out how it works and how well it works and what the implications are, and whether or not these things can be made much in the future much more sophisticated than we know of now. So in this talk I will cover leaked classified information from the ANT catalog. I don't think I put any screenshots in here from the ANT catalog, but I'm going to talk about things that I've observed from the ANT catalog. So if you don't want to hear about leaked classified information, you can leave now. Anyone for a game of Spot the Fed? I am going to show you in this talk a few hardware designs for my own retroreflectors, and I'm going to tell you how to build your own retroreflector right here at DEF CON if you want. I'm also going to do a live demonstration, and really kind of the reason I'm doing all of this is to lure you here so that you can listen to me rant about the state of emission security. Emission security is the field of security where we study emissions from devices, and a fair bit is known in the public research community, the hacker community, about passive attacks, but not very much has been known historically about active attacks. And today I'm talking specifically about active attacks, where an attacker actually transmits something towards a target. The passive attacks that we know about, you may have heard the codename Tempest. And sometimes people apply the word Tempest to kind of all of emission security, but really it's a code name that relates specifically to unintentional emissions. Now there are all kinds of different unintentional emissions. There are RF emissions, there are conducted electrical emissions, thermal emissions, audio, all kinds of things. There are all these different little side channels where somebody might be able to pick up some kind of an unintentional emission and from that information figure out something about the state of the target, and in some cases figure out extreme information about the state of the target, like reproducing what's on a video screen or capturing keystrokes and so forth. So there's a fair amount of research in the area of passive emission security attacks, and if you want to get started reading about these things, probably the best place to start would be the writings of Marcus Kuhn. I do think there is quite a bit of opportunity in the field of passive emission security for future research. There are lots of things that are unexplored at this time. However, we at least have a little bit of information and a little bit of public research, and you can find papers. That's not true so much for active attacks. Active attacks, the main thing that we've known about for years that everybody always talks about being the prime example of active emission security is the thing, the Great Seal bug. This was a bug that was discovered inside a wooden carving of the Great Seal of the United States in the U.S. Embassy in Moscow. And information about this bug was released publicly in 1960. It was supposedly discovered in the early 50s and may have been implanted as early as 1945. So this is technology from the mid to early 40s. And it's an incredibly simple device. It consists of a microphone and an antenna, and that's it. It doesn't have any active components whatsoever. It simply is a condenser mic, which is a capacitor that changes its capacitance based on the air pressure. And that is connected to an antenna in such a way that the air pressure, the changes in the air pressure, which of course changes in air pressure are sound, the changes in the air pressure modulate the impedance connected to the antenna, and that modulates the reflection that comes back to a radar unit that is illuminating this device. In some ways, it is very difficult to detect because it's not active most of the time. You wouldn't, if you looked around to try to see, like before a big meeting, if you went around looking for any bugs that were transmitting, you would pick up nothing from this thing. But once the meeting starts and your attacker starts illuminating this device with the radar, then suddenly it is active. And it uses no power, no local power supply whatsoever. And it's a pretty incredible invention for the time. The next thing, I think everybody's heard about now, that we've had these RF retroreflectors in the ANT catalog. And so what happened in between the thing and the ANT catalog? We had 53 years of rumor and speculation. And I wish I were exaggerating, but really, if you look for hard evidence, if you look for example designs, if you look for somebody who's done an actual experiment to show how an active emission security attack works, you'll find almost nothing between 1960 and 2013. It is such an unbelievable gap. We are decades behind the intelligence agencies in our basic understanding of threats against our own systems. And now some people will argue with me, some people will say otherwise. They'll say, oh, I know all about these active attacks, and they'll rattle off some code words, and they'll mention some declassified documents, and you know, I say to them, POC or GTFO. Because, yeah, we've had a lot of hints. We've had a lot of hints from declassified documents over the years. We've had a lot of speculation, but show me the one place where somebody's done a research paper. Show me the one place where somebody's given a conference talk, released a hardware design, done an experiment, published the results, and I personally haven't found any. I'd love it if somebody just like ran up here and proved me wrong. That would be amazing. But I've been looking and I haven't found it. Now, one thing I found, a brief mention in the paper Soft Tempest by Marcus Kuhn and Ross Anderson. They do mention an attack where a keyboard cable, a computer keyboard cable, was irradiated, and key presses were detected by the return from that cable. Now, this I would put in the category of rumor and speculation because it's just one brief mention in a paper about other things, and it comes from a declassified German document. With, as far as I know, no one's ever actually tested this in a public experiment. But one of the interesting things here is that this was apparently irradiating or illuminating an unmodified keyboard and cable. Unmodified. No implant was intentionally installed in the target. The equipment out of the box was vulnerable to this attack, which is quite interesting to me. And there are some hints in the Ant catalog that suggest similar attacks are possible on other things. For example, there's a VGA video implant that is a retroreflector for picking up the video signal. And on the page describing that implant, it says that it provides an enhanced return, which suggests to me that they get some kind of return sometimes from VGA cables without enhancing it. That's very interesting, I think. Post-Ant catalog. Just this year, there have been some public on YouTube some experiments that this one person, GBPPR, has posted. So I recommend you check those out. As far as I know, he and I are the only people who've been playing with this stuff and talking about it publicly. So today, I'm releasing open source hardware designs for actual implants. And I'm teaching you how you can build them yourself and how simple they are. And I'm going to do a live demonstration on stage, which hopefully will work. I mentioned just a second ago that there may be capabilities, maybe possibilities of making this kind of retroreflector attack work without actually implanting a target. And so I would consider that a case where we have an unintentional retroreflector, which is my bottom row there. There's also the case where there's an intentional retroreflector, where we have some kind of an implant that we install in the target. And then there are other cases in these columns. What I'm doing today is I'm intentionally illuminating. I'm firing a radio wave at the target. But there are also potentially other cases where a target could be unintentionally illuminated. Like, for example, everybody's walking around carrying mobile phones that put out far more radio energy than my test systems up here. So if you're walking near a device that is vulnerable to this, or is implanted so that it's vulnerable to retroreflection, then you may be unintentionally illuminating it and causing it to create a reflection that an attacker can pick up. And these types of attacks, we've seen hints of, we've heard rumors about, but I don't know of any research into any of these categories, really. I don't know of any publicly demonstrated experiment like, except for what I'm doing today, just in that one category. So this is a wide open research area. There's a lot of opportunity. And what I'm doing today is only scratching the surface of that one square in the grid. A quick note about the term retroreflector. In the Ant catalog, it's spelled with a hyphen, but I don't know why, because if you look around at other literature, you'll find that it's actually a fairly common technical term without the hyphen. So I've adopted it without the hyphen because that seems to be the common usage everywhere other than the NSA. But I am adopting the term retroreflector, which is a little bit of a stretch maybe. I mean, the word retroreflector means reflecting something back to its source. So for example, when you drive down a highway and you're at night and your headlights hit a road sign, the road signs have a retroreflective coating on them so that most of the light from your headlights comes back at you, and the road signs look very bright. But somebody standing off to the side of the road who's not back near the source of light doesn't see the road sign illuminated so brightly because of that retroreflective surface that somehow reflects that light back towards the source that it came from. And this technology, if you want to see a really cool application of that and of optical retroreflection, the CAST AR project is doing a wonderful augmented reality sort of system that takes advantage of that type of optical retroreflection. So a radio retroreflector, in my opinion, would reflect most of the energy back towards the source. And that doesn't actually appear to be what the devices in the Ant catalog are doing. They appear to be using very small, not very directional antennas. And so they're reflecting, yes, but they're kind of scattering energy in a lot of directions and not particularly back towards the source. Now, with bigger, more sophisticated antennas in the implant, they could be more retroreflective. So just be aware that that term is used a little bit loosely here, but I've adopted the term RF retroreflector just because that's what they're called in the ant catalog. The method of communication is more commonly called RF backscatter communication. And if you want to find out more about how this method works, then backscatter is probably more the search term you would want to use instead of retroreflector. There is a lot of public research on RF backscatter communication. Can anybody tell me the year of the first paper on RF backscatter communication? Does anybody know it? Nobody? I'll give you a free retroreflector. I didn't hear it. Sorry, guys. 1948. 1948, there was a paper called Communication by Means of Reflected Power. And realize that this was after the thing was probably deployed. So the very first public research paper on this means of RF retroreflection or RF backscatter communication didn't happen until well after the thing was deployed. So that thing was a pretty cool invention for its time. Now there was research into like optical backscatter prior to this, but this is the first paper I can find on RF backscatter. There's a lot more research over the years since 1948, and in particular over the last couple of decades, if you look for any UHF RFID technology, UHF is a range of frequencies that's used by the RFID tags that get longer distance, longer range. The really close range, the stuff that you have to have very close proximity for, is down in the low frequency LF or HF. UHF RFID tags are a little bit more similar to the type of thing that I'm using and the NSA seems to be using. In fact, most of the NSA implants seem to be working in the UHF band. So if you look at designs for UHF RFID tags, they're very similar to the type of design you would want to use for building a retroreflector. Now, I have to have a retroreflector, but I also have to have a radar system. I have to have a means of firing or a radar beam or illuminating a target and then picking up the return from that target. There's plenty of off-the-shelf radar gear. A lot of it's pretty expensive, but you could find things like a police radar. I've got a police radar, an old police radar off eBay for, I don't remember, like $50 or something like that. It's not that much. However, police radars are typically up above 20 gigahertz, which is an order of magnitude higher frequency than the NSA seems to be using based on the ant catalog. So maybe that's not the best approach. One of my favorite devices is the Hot Wheels radar gun. You could find these on eBay for about $25, and they operate at about 10 gigahertz, which is, you know, at least closer to the frequency range that I'm interested in. And they're just fun to play with. The device is made up of kind of three separate parts. There's a battery compartment, and then there's that waveguide antenna, that big tube, and on the right-hand side of that there's a circuit board. And then there's a separate circuit board on the back with the microcontroller and the LCD. The microcontroller board is the part that typically fails. So if you get a broken one, it doesn't matter, because all you really need is that radio board that has that little black cable coming out of the back of it on the right. And that little black cable has 3 wires in it, and all you have to do is apply power to it, and you get a baseband signal on the third wire. And you can plug that into an oscilloscope, or you can plug that into a HackRF, or into a sound card even, and measure the return that it's getting. So it's a pretty cool device for experimentation. You know, it's really easy to add that baseband output, and I recommend checking out this website if you want to find one of those and learn how to take it apart, which is a annoying. There's also, I've noticed, quite a few devices that you can find that are very similar to the Hot Wheels radar gun, but are in a smaller package. They don't have the whole big waveguide antenna, and they don't have the plastic and trigger and everything. And they're designed as modules for people to use in their own electronics projects. If you search eBay for Arduino radar, you'll find a lot of these things like shipping from Hong Kong, and they're only a few dollars. So that's an interesting option. But again, they're at the like 10.5 gigahertz band, which is higher than the devices in the Ant catalog. The coffee can radar is pretty cool, from Greg Charvat and various other friends who have posted information about that design or that family of designs. There was a talk here at DEF CON a few years ago on the subject. It's cool, except it's typically used with capture, baseband capture using a sound card, which is very low bandwidth and isn't sufficient for some of the targets, the higher bandwidth targets that I'm dealing with. So it has potential. Also, it has some circuitry to do FM CW radar, which is more complicated than the simple CW radar that is all you need for this type of application. So what I'm doing primarily is using HackRF1, which is my own design SDR platform. By the way, if any of you backed HackRF on Kickstarter, I'm happy to announce that they have all shipped. Yay! Woo! Although some of the shipment notifications have been delayed, but the units are actually shipped. So I'm using HackRF primarily, which is a software-defined radio peripheral. It connects to a host computer typically. It's open source hardware, so anyone can build this, anyone can extend this design, and I think that's important when doing anything science-y. The official operating frequency range is from 10 megahertz to 6 gigahertz. If you want to know a thing or two about the unofficial operating frequency range, come to my talk at the Wireless Village tomorrow. The bandwidth, the baseband bandwidth is 20 megahertz, which is like 3 orders of magnitude higher speed than a sound card. So I was talking about how a sound card input really isn't fast enough for some of the targets that I'm interested in. 20 megahertz is quite a bit of bandwidth. It's not as much as the Ant catalog radar devices, but it's enough to be able to do some really interesting experiments. And it's a half duplex transceiver, which means I can transmit or receive, but I can't do both at the same time, which is why I have 2 units up here, one to transmit and one to receive. So my super sophisticated cardboard test apparatus holds 2 HackRFs and 2 directional antennas, these PCB antennas. I've actually split this up here so that I can have these antennas pointed at different directions. Instead of being parallel, I can make like a triangle out of them, and we'll see how that goes. And I'm using a frequency of 2482 megahertz, 2.482 gigahertz. It's right at the top end of the ISM band, the 2.4 gigahertz ISM band that's used by Wi-Fi and Bluetooth. However, it's just above the frequencies used by Wi-Fi and Bluetooth in the US. So there's a little bit of room at the top of the band that isn't getting used by a whole lot. And the NSA, according to the Ant catalog, is using frequencies in the range from 1 to 4 gigahertz. So this is kind of right in the middle there. And it just so happens that that range happens to be in the kind of center area of the HackRF, where I get the best HackRF performance around the 2.5, 2.4 gigahertz. That band is where I get the best performance. And it's also easy to find off-the-shelf filters and amplifiers if you want to experiment with amplifying these things, for example, although you have to be very careful about that. I'm actually using unamplified HackRFs for my demo up here today. So this is a pretty good operating frequency, and it's what I've done most of my testing at for this variety of reasons. The first retroreflector that I built is called Conga Flock. I don't know if you guys can see it very well, but up there across the top, those numbers are centimeters. And between those two orange pieces of wire, there's a little tiny circuit board. Now, I bet I know what you guys are wondering. You're wondering, how in the world did this thing get to be so huge? It's giant. So it's giant for a number of reasons. And now the first retroreflector I made, the very first one, was just a bare transistor that I soldered some wires to. And then I decided, well, it's good to have a PCB, a substrate that kind of holds everything together and gives it some mechanical stability. And then I wanted to have a few extra components so that I could experiment with some things that I'll talk about in just a second. And then, even after doing that, it turned out that the circuit board was less than half the minimum size requirement from Osh Park, my favorite PCB maker. So I had to like double the size, but at least that gave me some room to put some silkscreen text on it and give it a little bit of a handle so I can put it into my bench vise and work on it a little bit. So I'm going to go over the hardware design here, and I usually don't go over electronic schematics in detail in a talk like this, but this one is simple enough that I think it's worth going through in detail. The first thing you need to know is that thing in the middle, that funny looking thing, Q1, is a MOSFET. That's a type of transistor. And then all of the various long rectangles are resistors, or they're just places where you could put a resistor or some other passive component. However, that one on the upper right, R1, that's a do not populate component. It's just something I put there. It's a footprint I put there just in case I wanted to experiment with putting a different impedance in that spot. So we can just ignore that. That's not populated. And then these two at the bottom are not populated, but they have a little bypass through them that you have to cut the trace if you do want to populate them. So again, those two at the bottom are just there in case I want to change the circuit in the future. So we can ignore those. Those don't really exist in the circuit. And then that other resistor there, the only purpose of that 10K resistor is just to protect the gate of the MOSFET. And it doesn't really affect the way the circuit works much, other than providing that protection. And the MOSFET itself, the one that I'm using, or the ones that I'm using, typically have built-in protection. So we can ignore that too. And what we're left with is this incredibly simple circuit with an antenna connected at the top, the target device connected at the left, and a MOSFET in the middle. A MOSFET is just a transistor, and you can think of it as a switch. When the gate, which is the input signal from the target device, when the gate is going up and down in voltage, the MOSFET switches on and off the antenna. That's all this thing does, is it just switches on and off the antenna according to the signal that comes from the target. And that creates a change in impedance on the antenna that modulates a reflected signal from that antenna. So it's incredibly simple. It's a one-component circuit. And I can use this as a general purpose retroreflector and connect it into whatever device I want, as long as that input is swinging through a couple of volts at least. When typically target devices will often have voltages of like 3.3 volts or 5 volts, and that's plenty to drive this thing. So I made a few, and they were really small, so I made 1,000. If you want to make one, I have this whole kit together here that I'm going to deliver to the Hardware Hacking Village that includes the circuit boards, the MOSFETs, some wire that you can use for the antenna, and some wire strippers, cutters. And here's what you do if you want to build your own. All you have to do is, first step is break off a PCB from the panel. That's a little bit more annoying than it should be. They're not scored very well. But if you find a nice sharp edge of a table or something, you can break these things off. Then you cut 2 antenna wires, and you want to make them about 1 inch long for operation in the 2.4 gigahertz band. There's a nice little guide that I sharpied onto the bin here. And so just cut 2 of those, then you solder the MOSFET onto the board, and then you solder the antenna wires onto the board. And then you might as well solder the other 2 a couple of wires onto the other two little pin headers, because you're going to need something in there to connect to a target. So if you solder in a short little piece of wire, then you can clip alligator clips to it or what have you, or solder the other end to your target. So it takes a little bit of electronics know-how, and I apologize, these things are a little harder to solder than they could have been, and harder to break apart than they could have been. So if you do try this, you're going to hate me, but hopefully you'll have fun, or can at least take home a souvenir or something. And then I will solder it into something. So in this case, I took a PS2 cable from a PS2 keyboard, and I just spliced in the conga FLAC right into the middle, and I was able to get a return off of it that way. So flamenco FLAC was my next retroreflector, and it's taking this same design basically and putting it into a convenient form factor for experimenting with PS2 keyboards. So all it does is it has two PS2 connectors. You can kind of see one of them in the photo there, but I have one up here. It has two PS2 connectors and the little retroreflector in the center. So the actual circuit, if you look at those two antenna wires, there's a little black blob right next to them. That's the whole circuit, really. All the rest is just connector. And so if I'm going to sniff PS2, I'm going to be tapping either the clock line or the data line. The clock line we see in this diagram at the top, and the data line we see in the diagram at the bottom. Now ideally we would tap both to recover the data, but I'm only going to tap one, and I'm going to tap the data line. And what we have here is a diagram of what the voltage on the line should be for the letter Q if somebody were holding down the letter Q on a keyboard. And so I'm going to see if I can sniff this using flamenco FLAC. Let's see what happens. I'm just turning on my HackRF to transmit like a couple seconds at a time at 2482 megahertz. And then I'm using my other HackRF with this flow graph, not this one, this flow graph here. And the long and the short of it is I'm going to be picking up the signal and doing an amplitude demodulation. So I'm doing AM demodulation. Let's see if this all works. Now, my I think I'm getting a signal out of it. Now, if I were to adjust my target here so everything is well lined up, I'm firing a signal at it with one of these antennas, and I am detecting a signal from it from another antenna. And I'm running a little short on time here, but hopefully this works. I'm going to look at triggering this. This is basically an oscilloscope that I'm looking at, like a software oscilloscope. And see what happens if I hit some keys. Oh, I'm getting something changing, but it's not looking very good. So this is a total demo fail. Probably because I spent all last night trying to raise money for the EFF, and I spent all this morning trying to help kids solder LAN taps at the Roots Asylum. I think I actually got something. I'm going to change my counts per division here, and oh, there we go. Let's see what's going on. If well, you're not actually seeing what you should be, so don't clap yet. It's really close to working. Now this is a little bit finicky because I have highly directional antennas, and if they're not aimed very well, then this may not work particularly well. I'm definitely getting something, but I'm not sure that I'm actually getting, like, you're totally not seeing the letter Q yet. So I'm just going to show you a screenshot from a previous run and move along. Previous run I did looked like that. And do you notice those 3 downward pulses and then the 1 wide pulse? Right? This is what it was supposed to look like, and it looks like that. It's very recognizable. So I'm running short on time, so I'm not going to be able to do a better job at my demo, unfortunately. I'm going to show you the rest of my retroreflectors. Tango Flock is a retroreflector for USB, and I've used it to monitor USB keyboards in particular. Because they're low-speed USB devices. So I've briefly tested low-speed devices, and I've figured out that yes, I'm getting a signal with characteristics that looks kind of like low-speed USB, but I haven't actually decoded bits, although I have decoded bits from the PS2 cable. Full-speed USB, which is kind of the next step up in speed, probably works with this implant. I doubt that high speed would work, and you would need a much higher bandwidth collection platform than HackRF. Super speed definitely doesn't work. You would need some kind of incredible system for that, and I don't even connect the wires. So Salsa Flock is the next one I have, and the DEF CON speaker ops were totally awesome to get me a VGA, an extra VGA projector, and I'm totally not going to use it because I'm running out of time. And it probably wouldn't have gone any better than the PS2 demo. But I have this little device, and again, it's a fairly simple circuit that just gives me some big connectors that makes it convenient for experimentation. This circuit is a little bit bigger. It has more components in it. The reason for that is that VGA signaling is lower voltage. And there isn't enough voltage swing in the VGA signal. It's too low voltage to kind of trigger the MOSFET's gate. So I have to do some biasing of the MOSFET to get it up to voltage. But I'm happy to report that I have gotten to the point with this where I can detect a signal from I can detect a VGA signal, and I'm in particular tapping the red signal. And I can actually very easily detect the vertical sync happening like every 60 hertz or something if I refresh, and I can definitely see patterns within that. So there's some potential for recovering the image on the screen. Now, how much of an image I can get with only doing 20 megahertz sampling that I'm doing with the HackRF, I haven't determined yet. It may only be very useful when the target has a low screen resolution, which means it has a slower pixel clock. And you would need a higher speed sampling rate in order to target higher screen resolutions. But this is an image, this is just a plot. And you see each of those, of the AM demodulated signal that I got from Salsa Flock. And you see those tufts there, those individual kind of tufts at the bottom? Those happen 60 times per second, and this was a 60 hertz screen refresh, so that's where I was definitely seeing the vertical sync. Now, I don't have a whole lot of time to talk about countermeasures, which is probably a good thing, because I don't have a whole lot to say about countermeasures. I don't think that we know enough about these threats yet to develop good countermeasures. But we need to think about how we validate that our equipment works, how we evaluate that it hasn't been modified or had things implanted in it. We need to know, are we being illuminated or irradiated by things? And are our devices prone to retroreflection without being implanted? And we don't know any of those things. We have a lot of research to do to be able to do that. But there is a talk in the next hour by Lei that looks interesting. He's kind of taking a higher level view of the problem and trying to figure out how to detect this stuff. I want to invite everybody to play along. An invitation to hack. I would love it if people built some of these here and started experimenting with them. I would love it if people took my designs from GitHub and started to build some of their own. We're going to have some, if I solder some up this afternoon, we'll have a couple over at the Hack 5 table in the vendor area. Darren was kind enough to give the NSA Playset crew a little space there. And other folks who are doing NSA Playset talks are also going to have some things there that we're just trying to get tools out to people if we can. And of course we had the EFF Summit last night. And I just want to remind people, there's a big open field of research. Do be a good neighbor if you experiment with this stuff. Know your laws. Try not to interfere with people. Doing low power experiments is very easy to do. You know, I've done PS2 sniffing from 1 meter with unmodified hack RFs that transmit at much lower power than your Wi-Fi card in your laptop. So coming soon, later this weekend, Mike Ryan's giving a talk in the Wireless Village tomorrow on some really cool Bluetooth smart stuff. These are all NSA Playset talks. Josh and Teddy are doing a talk on I2C implant, which is very interesting, and how they can expose or get to your I2C without even opening up your computer. GSM, NSA Playset GSM from Dean and Loki on Sunday, and PCI Express from Joe and Miles on Sunday. All of these I'm really excited about, and I hope you'll check them out. Thank you to Dean for coming up with the name the NSA Playset, and for the whole NSA Playset crew. Everybody's been great, and you know, it's a loosely knit group where we just take anybody who comes along and has a ridiculous name for a fun project. So please join us, and you know, if you have something that you think fits in the NSA Playset, we'd love to hear from you. And thanks to Jared Boone for helping me troubleshoot some of my retroreflectors not too long ago. NSAPlayset.org is where you can find information about all of the NSA Playset. My retroreflectors are on GitHub at that URL. I recommend waiting just a few days before you download and have PCBs made, because I do have a couple of minor corrections that I need to make. They're pretty minor though. They're things that you can fix very easily with a soldering iron. And my URL for is greyscottgadgets.com. So I'm going to have a little Q&A session out by the pool in, let's see, 15 minutes. So, you know, after I leave here, go look for me at the pool. I'll be wearing this awesome NSA Playset t-shirt that says, "My X key score goes up to 11. So if you see anybody wearing these shirts, they're probably people who are doing awesome NSA Playset stuff, or they're people who supported the EFF last night. So either way, they're probably cool people to talk to. Thank you all for coming.